I would like to invite you all to have a look together with me at why classification can help regression, if this happens at all. We start this work from the observation that some of the literature, computer vision literature, adds the classification laws to the regression laws for solving regression problems by binning the regression targets into a fixed number of bins and optimizing jointly these two losses. The question is, why would this be beneficial? To answer this question, we start from a simple one-way function. We bin this function into equally sized bins, which we call classes, and then we again also optimize the simplest case. We add weights to the regression laws and add the classification laws to it, and do the optimization jointly. And then we ask the question, what can classification add to regression, if anything at all, and are there scenarios where adding classification laws can be beneficial in optimizing the regression? For this, we start from 10 randomly sampled functions. They are a sum of two sinusoids with different frequencies and amplitudes, where the x values are sampled between -1 and 1, ending up with targets between -1.5 and 1.5. On this data set, we consider three scenarios. We consider clean data scenario, where the function is just as defined by the equation. We add noise to the target, so creating a noisy data set. And we sample the function from different regions on the X space during training, and different regions for the validation and test set to create an out-of-distribution scenario. We also vary the sampling of the function, so we start from uniformly sampling the function along the targets, the y-axis, and then we consider the mildly imbalanced sampling, where we sample more from a certain region, then moderately imbalanced, where this region becomes smaller, and severely imbalanced, where this region is even smaller. We vary the region that we select for the imbalanced data, and we repeat the sampling with 5 different seeds for the uniform case to create 5 different versions of each of these data sets. We then run experiments by varying the number of classes from 2 to the power 2 to 2 to the power 10. So we have 5 different classes, and then we run experiments on all the data scenarios and sampling scenarios we have mentioned for all these 10 functions. We train 3-layer MLP with relevant nonlinearities and estimate mean squared error at the test time. And we observe that for the clean and the noisy data scenario, there is a slight improvement while adding classification laws to the regression laws, so the green line compared to the red line. And in the paper, we try to formalize these observations starting from the derivations of Renton. Next to the synthetic 10 functions we considered, we also evaluate on the real data. So we use a depth estimation data set from 31 and the age estimation data set also from 31. And we evaluate if the same effect of adding a classification loss to the regression loss is present. And we see that also on the real data, there is a tiny bit of improvement to be observed. Also, we consider video progress prediction on the breakfast data set, where we add again a classification loss to the regression targets, and again we see a tiny bit of improvement. Of course, our analysis is not without limitations. We do not consider a lot of other hyperparameters that could affect our findings. So model size, depth of the model, the choice of the optimizer, the loss function, maybe a better optimized, regularized op function. A loss function could actually make these effects disappear. So I would like to encourage you all to have a look at this problem and maybe disprove it or come with a better explanation or deeper understanding of what's happening. But here we present a preliminary analysis of the effect of adding classification laws to the regression laws, and our findings that this seems to be the case if the data is imbalanced. Thank you all, and come by the poster and check the paper on arXiv.